Okay, so now what I'd like to do is I'd like to solve an example that demonstrates the stress-strain curve modeling idea, and I'll do that with the elastic power hardening model. We could certainly also employ the Ramberg-Osgood relation. We have there some nonlinear relation between stress and strain. We could certainly use it. It would perhaps require a tiny bit more effort, but instead I'm going to use the elastic power hardening model, and it's also a good way to demonstrate complications that can arise when we try to determine the material parameters so as to fit experimental data. Okay, so first of all, we need the data itself, and I'm going to quickly depict the data over here. Okay, so this is our stress axis, let's say MPa, and then the strain. Careful, I'm writing the strain in terms of percent. Eventually in the model we have to put the actual value of the strain, and I do need some grid lines here to guide me through what I want to do. Grid lines are not perfect. That imperfection also eventually will help us highlight some difficulties that often arise when we try to interpret experimental data. So in this case, it's a sort of a spurious effect, because I could certainly draw this better, but nevertheless, as I said, I think at this point we have some useful information already to extract from this crude depiction of the stress-strain curve, or the data. Let's say the data is offered somehow through a number of points that I'm going to take as a guide here. So that's one point, and it's another point. Okay, let's say I have some data points, and from those data points I'm able to draw a line that looks like this. All right, and I do need the values. This is 0.4, 0.8, 1.2% strain, remember, 2.0, 2.4, and the stress values are 80, 160, 240, 320, and 400. Okay, so I would probably need to also describe the problem. So we have an alloy, and it undergoes a manufacturing process that changes its mechanical properties, right? If the manufacturing process involves deformations, we know, for instance, that the yield strength, the ductility of the material is going to change with deformation. It will significantly harden, etc. We've discussed these before, and therefore, as soon as the material undergoes this manufacturing operation, manufacturing process, then its properties will change, and I need to somehow determine the new properties. Now, what probably will not change is the Young's modulus, but still I'd like to be able to extract that information through the experimental data that is provided. So I'd like to find E, and I'd like to find sigma naught. And I'll do the latter one by making use of a model. In this case, the elastic power hardening model. Okay, so first I will go ahead and solve part A, right? So I don't quite have a distinct yield point. I certainly could have used the Ramberg-Osgood model, but I will eventually use elastic power hardening. But I can see that in that region probably the curve is almost flat, and I can pick 2 points. I can pick point B and I can pick point A, and then I can identify the Young's modulus as the stress at B minus the stress at A divided by the strain at B minus the strain at A. So the stress at B, let's write that over here. So the strain is, now here's the bit of difficulty that we are going to face. So we have to be careful about how much resolution we put into reading this data, because my grid is quite widely spaced. But I'm going to say, perhaps with some flexibility, that, well, midway is 0.6, and that would be that point, and so 0.5 would be that point. It's still not very close to my point, so I'm going to assume that this point has 0.45% strain, and the stress is 160. Okay. Now for this point, it's lying almost at a value of 0.2, so I'm going to say that the strain is 0.2% and the stress is 80. And now I'll go ahead and calculate the Young's modulus. So it is 160 minus 80, everything is in MPa, divided by 0.45 minus 0.2, but remember that these are percent strains. I need to divide by 100 or multiply by 0.01 to convert them into actual strain. And if you do that division, 80 times MPa times 100 divided by 0.25 will give you about 32 GPa. Okay, so the Young's modulus is 32 GPa. That's good. That's something I have to know whether or not I'm going to use the elastic power hardening model. I also need it for the Ramberg-Osgood relation, and I also need it for a visual determination of the yielding, because eventually if I want to, let's say, use the 0.2% offset method, I need to draw a line that is offset by 0.2% strain and with a slope of 32 GPa, right? Now, if you do that, exactly that, right? And that now takes us to point B. If you do 0.2% offset, let's see what we're gonna get, okay? Because that's certainly one way with which I can determine sigma naught. So 0.2% offset, what I have to do is, first of all, my elastic loading line is this, and of course I don't proceed along that line. At some point there is some plasticity, significant amount occurring, so the red line is actual data. But then what I would do is I would draw a line that is offset by 0.2%, and that is exactly 0.2%, offset with the same slope, such that it goes and intersects the red curve. And the point of intersection would be the yield strength. So the way I have drawn it, perhaps I haven't done it very accurately, but I'm going to say that the yield strength here is about 320 MPa. Okay, so with the 0.2% offset method, that is how I could eventually calculate or predict the value of the yield strength. But alternatively, we can use the power hardening model. Okay. The power hardening model says that, well, if I am in the elastic region, sigma is equal to E epsilon, there is no free parameter there. If I'd like to eventually find the material, or if I can somehow find the material parameters H1 and N1, then when sigma is larger than sigma naught, that relation needs to hold. So I can somehow, using the data, I can determine the parameters H1 and N1. And once I find those, together with the knowledge of E, I can also predict sigma naught, remember, because there's a relation that relates E, H1, and N1 to sigma naught. And that's the way I'm going to proceed. So beyond the point of yielding, sigma is equal to H1 epsilon N1. And I'm going to try to use the data to determine these unknown material parameters, and afterwards predict sigma naught through the relation E H1 over E to the power 1 over 1 minus N1. Again, this relation is not something you need to memorize, but you certainly need to remember how to derive it. It's fairly easy. Okay. Well, what I'm going to do is I have conceptually two constants to determine, and I'm going to take 2 points and generate 2 equations for 2 unknowns. Okay, so of course there is a caveat here, a point that we need to be careful about, and that point is that the point I'm going to choose, the 2 points with which I will generate 2 equations for 2 unknowns, they have to lie in the region where plasticity occurs, but I don't know the value of sigma naught yet. So I'm going to assume that the points that I pick actually do lie in the plastic region. So it is yet unknown, and that's a difficulty. So I have to assume the following 2 points lie in the plastic region. Okay, so I'm going to pick a point, let's say point C, for which the stress is 240 MPa. So I'm roughly here, 240 MPa, and the corresponding strain is 0.007. That's something that I'm reading from this plot. So point C is roughly there. Okay, that's point C. Then I pick another point. I pick point D, and point D is such that it has a stress of 400 MPa and a strain of 0.018. Okay, so that's 1.8% strain, about there. Okay, that's point D. All right. So the red line passes through those 2 points, and therefore eventually my model should also be able to replicate that data. And I'm going to now force my model to satisfy these 2 points. In other words, I'm going to force it to pass through those 2 points. So that's point D. So I'm going to say that sigma c is equal to h1 epsilon c to the power n1, and also sigma d is equal to h1 epsilon d to the power n1. Now what I can keep in mind at this stage is this a typical power relation. The relation is in power form in the actual coordinates, but if I take the logarithm of both sides, this can be, let's say, the natural logarithm, then this becomes a sum, ln h1, plus the exponent becomes a factor, ln epsilon. So all of a sudden, I convert the information that is in power form to information in in linear form, because ln sigma is now like a parameter y, ln epsilon is a parameter x, ln h1 is like a constant a, and n1 is the slope of the line in the logarithm strain versus logarithm stress space. Okay, so now therefore when I talk about these relations, I'm going to talk about them in this form after taking their natural logarithm, which means I'm going to go ahead and take the natural logarithm of sigma c, which is 240 10 to the power 6. ln sigma is equal to ln h1, which is a. That's what I defined it to be presently, just for the purpose of this example, and 1 ln c. So ln, and that's going to be in absolute value, not in percentage form, so 0.007. Then that was for point C, and then for point D, we have ln 400 MPa equals A plus N1, and the corresponding value of the strain. And that's nice. Now I have two equations for two unknowns. I can simplify this for you. This here, it turns out, is equal to 19.296. This one here is 19.807. The ln of 0.007 is minus 4.962, and ln of 0.018 is minus 4.017. So you have two equations for two unknowns, and you can solve for A, and so after solving, you will find that A is equal to 21.98. Remember, A is ln h1, and therefore h1 is e to the power A, which corresponds to a value of 3.516 GPa. It's a little bit too high, and so is N1, 0.541, certainly less than 1, but larger than the usual maximum value that is observed. The usual value is about 0.4, but still, this is what I have. These two values of H1 and N1 eventually are such that with those values, if I plug in epsilon c, I will get sigma c. If I plug in epsilon d, I will get sigma d. So my relation model for sigma versus epsilon certainly passes through points c and d. Now, you should keep in mind that this is a very crude way of determining two parameters that replicate experimental data, the red curve, as well as possible. I'm just picking 2 points and trying to make sure that my model satisfies those 2 points. A better way to do this is to eliminate the effect of the choice of the points, because if you were to choose 2 other points, you would get 2 entirely different constants. If you choose a lot of points and try to make sure that my model is able to remain as close as possible to all of those points, it's called the least square procedure, and that least square procedure is a better way to determine free parameters in a model in such a way that the choice of the points do not really play a significant role. Okay, am I done? That's the question, right? Am I done? Because I have determined H1 and N1. Now I can go ahead and plug them in that relation. I know what E is and I can determine sigma naught. And I've done multiple things now presently. I have now a model that is able to predict the value of stress for any given value of strain. Now, when I plot stress versus strain with these values, it won't look like the red line. It will pass through C and D. You can go ahead and try to see what it looks like and take visual data points from the red line and compare the red line with the prediction of this model. The model beyond the point of yielding will match only points C and D on the red curve, but not the other points. So nevertheless, it's a model, okay? And I have some modeling error, but it's a model and I can also predict sigma naught. But am I done? Now, the point is I'm not done because I have made an assumption. And whenever you make an assumption, you need to go and check whether your assumption was correct or not. So to make that check, first we go ahead and predict sigma naught. And that relation tells us that sigma naught is 260 MPa. I get that by plugging H1 equals that and N1 equals that value together with E into that equation. I get 260 MPa. And I notice now that sigma A is larger than sigma naught. Okay. Sigma C is supposed to be larger than sigma naught because this model works only if stress is larger than the yield strength. And I've chosen a point C and I've assumed that this holds. But it actually does not hold. Why does it not hold? Because this is 240 and this is 260 MPa. And therefore my assumption was wrong, and I really need to now at this point go back and get rid of this discrepancy. I need to go back, pick a point, not C, not here, perhaps further into the plastic region, and then reiterate this process until I get rid of the discrepancy or I get a result that is consistent with my assumption. Okay, so I specifically chose the elastic power hardening model to illustrate this difficulty. Sometimes to determine the model parameters, you have to make assumptions, and at the end of the day, you have to go and check your assumptions. And if it's not satisfied, you have to reiterate. If it's satisfied, you're done. Are these perfect values? No. With these values, you will pass through points C and D, but not through other points on the stress strain curve because this is just a model. Okay, notice that if I had used Ramberg-Osgood, I wouldn't have to check for a sigma naught value because Ramberg-Osgood is not working in an on-off manner. For any given value of stress, there is always a plastic strain and therefore there is no distinct yield points. I can still calculate the yield strength through the 0.2% offset method, but I wouldn't have to do any checks. So you can go ahead and try yourselves to see how Ramberg-Osgood would work in this scenario. So with this now, we are actually done with the topic of plasticity, and this was our first exposure to a detailed modeling effort, in other words, relating strain to stress beyond the point of what we called failure earlier, beyond the point of yielding. So now I can also predict what happens well into the region where plasticity occurs.